Today I'm going to talk a little bit about three-phase induction motor, which is an important topic of electrical machines for electrical engineering in GATE. Okay, so in this particular topic I will try to speak or talk a little bit about the speed control technique of this induction motor. But before I start, I want to talk about the basics of or the working principle and the approximations that we take while we analyze the three-phase induction motor for the speed control applications as well as other applications. Okay. Now you see the exam or the GATE exam which we have. At that point of time, we have to realize one thing, that in this particular motor, we are eligible to take a very good approximations. Okay. Why? Because we can take approximations, and if we do not take these approximations, our analysis will become very complex. Okay. So as a good electrical engineer, we are expected to take best approximation cases. Okay. And in this particular lecture, I will concentrate on how to take those approximations, which makes this particular analysis of induction motor for GATE very easy. Okay. Now you see, if we go through the books which are like Bhimra or any standard books, in those books actually they cannot take approximations. Okay, because they have to maintain the practical situations. Okay, and in those books they have to give the exact situations. Okay, where practically, if you see the torque slip characteristics or the torque equation, okay, where the stator resistance cannot be neglected. They do not neglect in Bhimra, if you see, or in any other book, they cannot neglect that. They have to consider. Whereas in GATE, if you see all the questions throughout the years, they will mention that you can take the best approximation circuit, or they will even write in the question that neglect the stator impedance or stator resistance and stator reactance. So the moment you neglect this particular thing, or the drop in the stator, the analysis becomes really easy for you. Okay. So this is my effort will be there to realize the approximations. So let us see how we can do that. But before that, let us have a review on how the induction motor works. Okay. So in my earlier lectures, I have told that there are relationships between current and magnetic field. There are 4 relationships, and I will be using those 4 relationships in defining the working principle of three-phase induction motor. Okay. Now in this three-phase induction motor, we know that in books we have read that the stator will be supplied a 3-phase supply. So let us say this is my stator, and I have a 3-phase winding here. Let us say this is A dash, then I have B dash, and then I have C dash. Now this is called a 3-phase winding, where we have slots, okay, for 3 coils which are at a 120-degree phase difference. Okay. Now if we give supply to this particular slots, the conductors will be there, and to that conductors, if we give supply, what will happen is rotating magnetic field will be produced. Okay. In my earlier lectures, I have also explained how this rotating magnetic field is produced. So I do not want to concentrate on that right now. So what I will assume that I have a field. Okay. I have a field which is something like North Pole and say South Pole. So this is a 2-pole winding. Okay. So I am assuming that I have a North Pole and South Pole. Okay. And this axis, and let us say this is rotating clockwise. Okay, this is my direction of rotational magnetic field. Okay, so this is rotating clockwise. Now I want to show my rotor. Suppose this is a rotor, and let us say this is a squirrel cage. Okay. Now in this particular so suppose there are conductors in the rotor in this fashion, okay, and this is my field. Okay, this is my field here. The direction of the field is from north towards south, okay. So I need to find out what is the direction of the EMF which is induced. Okay, before that, we know whatever we read in books is that suppose this is an induction motor, okay, and it says that I have a rotational magnetic field which is rotating clockwise. So it says that due to Lenz's law, what will happen is, due to Lenz's law, there will be flux, due to Faraday's law, there will be flux cutting action. And due to Lenz's law, the rotor will start rotating along the rotational magnetic field so that the flux cutting action, reduces. Okay. So that is what is given. But there is one more way to look at it. Okay, the working principle. That means let us prove it. How to prove that actually the rotor will move along the direction of the rotational magnetic field. Now we have considered that our rotational magnetic field is clockwise. Now let us see how this rotor will start rotating clockwise. Okay, or why? Okay, let us see that. So the first thing that we can see at this is that these conductors I have considered a squirrel cage, rotor, and the conductors are short-circuited. So conductors here are short-circuited. That means if EMF will be induced, then current will flow in that particular conductors. Okay. So now what happens? You see, this is a field which is rotating clockwise, and conductors are present. So there will be flux cutting action. So if there is flux cutting action, EMF will be induced. Now this I have explained this in my first lecture. Okay. So you see, now I will give you, to explain this, let me give you one more example how EMF is induced. For example, suppose there is a north pole and south pole. Let me take this first simple case, that is a north pole and south pole of a DC machine. This field, okay, is static, and I have a rotor. These are A conductor and B conductor, and I have a rotor which is rotating clockwise. Okay. Now this rotor is rotating clockwise. Now I need to find out the EMF which is induced in this conductors at this particular instant. Okay. Now you see, if it rotates clockwise, what will happen? I can apply Fleming's right hand convention to find out the EMF which is induced. So you see the field is from north to south. So this is my field, and you see it is rotating. The force direction is clockwise. So I can say that this is the force direction. So if I open my third finger, I will see that the current through it is cross. Similarly, current through it will be down. Okay. Now this is simple. Now in this particular case, what is happening is the rotor is static, but my field is moving clockwise. Now I need to find out the EMF induced in A and B, which is in this particular case. Now, here you cannot directly apply this. Why? Because you see, here the rotor is static at the starting. Okay, at the starting this is not moving, but I have a rotational magnetic field, and that magnetic field is rotating clockwise. So if I need to find out the EMF which is induced in this rotor, first of all I have to see with respect to this, what is the rotation, what is the direction. That means you see, if a body, this is a body and this is a B body, if B is moving this side, okay, and A is static. This is the case. Now you see, if the frame of reference is B, then what B will think that A is moving this way. This is a simple example of a train. When you are sitting in a train and your train is not moving, but the other train is moving in the opposite direction, sometimes we feel that we are moving in the opposite direction, but actually what happens, the train is moving this side, you feel that you are moving forward. Okay, this happens. So this is relative motion. So what happens is these conductors, okay, for these conductors, the EMF that will be induced here, if the rotor is if the rotational magnetic field is rotating clockwise, they will think, or this field will think, that this rotor is rotating anti-clockwise. Okay, that means they are rotating anti-clockwise. He will think like that. Okay. So the EMF that is induced due to this field at this particular instant. So I know this is my direction of my field. Okay, and this is the direction of the force which is exerted on, or this is the direction of the motion which he is thinking. So what he will do, he will induce a EMF here which will be dot here. Similarly at this point, this is my field, and see, for him he will think that this conductor is moving this side. Okay, this field will assume that this rotor is moving this side, but actually he is static, he is moving this side, but he will think that he is moving this side. So in that particular case, if he moves this side, so what will happen, you see, the EMF that will be induced will be inside. Now you see, now we got the direction of the induced EMF. Okay, now we got the direction of the induced EMF. Now these conductors are shorted. So since these conductors are shorted, what will happen? Current will flow. Now we know that if in a magnetic field I have a current carrying conductor, force will be exerted. So this is the fourth principle what we have discussed in the first lecture. So you see, now let us find out the direction of the force which is exerted. Now to find out the direction of the force, I have told that we need to use Fleming's left-hand convention. Okay. Now you see, this is the direction of the field and this is the direction of the current. So you see, the force that will be exerted will be this side on this particular conductor. So the force that is experienced by this will be along this side. And similarly, the force that will be experienced by this conductor will be this side. So the two equal and opposite forces are exerted at distance. So torque will be produced. And you see, this torque is clockwise. So the rotor will start rotating clockwise. Okay. So hence we can prove, okay, by our laws and conventions that actually the rotor of the induction motor will rotate clockwise, or in other words, it will rotate along the direction of the rotational magnetic field. Okay, so this is the working principle of three-phase induction motor. Fine. Now, induction motor is all about, you see, relativity. Okay. Now, we also know that the rotor of the induction motor cannot, rotate at the synchronous speed. Why? Because the moment the rotor reaches the synchronous speed, the flux cutting action stops. And if the flux cutting action stops, EMF induced will be zero. So if the EMF induced is zero, the force that is experienced will be zero. So if the force is zero or the torque becomes zero, so what will happen? It will deaccelerate. The moment it deaccelerates, the speed reduces, and there is again some flux cutting action. So again the induced EMF is there, again some torque will be there, again it will start. So ultimately what happens is the average speed is always less than the synchronous speed. It cannot reach, or it cannot stay at synchronous speed. It may reach, it may reach instantaneously, but you see, the steady state will always be, or the average speed will always be less than the synchronous speed. Okay. Now let us see what is the difference between. So let us say the rotational magnetic field is rotating with a speed which we call ns. Now this ns is nothing but synchronous speed, and ns can also be calculated by the formula 120 into the supply frequency f of s by number of poles. Now this is the supply frequency, and these poles are nothing but the poles for which the stator is wounded. Okay, so this number of poles depends on how is the stator winding done. Okay, so suppose I have a 50 hertz supply and I have 4 poles. So the synchronous speed will be 120 into 50 by 4, which is 4, 330, 1500 RPM. So this rotational magnetic field will rotate at a speed 1500 RPM, or this is also called the synchronous speed for this particular situation. Okay. Now suppose we have a rotor here. The steady state at a particular load, let us say, this rotor is rotating at a speed called Nr. And we know that this Nr will be less than Ns. That means, let us say it is 1440 RPM. At a particular load, this rotor is rotating at this speed. Okay. Now you see there is a difference between them, and that difference should be there. Only if that difference is there, then the rotation can be sustained. The difference is not there, the torque will become 0. Okay. So now from this particular thing, we can say that I can establish a relation between this particular difference, and that is called slip. Slip, what we represent by S, is nothing but Ns minus Nr by Ns. So this is, you see, it is a per unit value. Okay, so it's a ratio, you can say. It will not have any unit, it's a per unit value. Or we can also say Ns minus Nr is equal to S into S. Or also we can write in terms of radian per second, that is omega S minus omega R is equal to S into omega S. So this is a relationship which will help us in analyzing the three-phase induction motor. Now let us also see a little bit about the equivalent circuit of induction motor. So we all know that equivalent circuit, you see, this will be the resistance of the stator, then reactance of the stator winding, and then magnetizing inductance, core loss, representation, induced EMF in the stator, and air gap. After this air gap, I have induced EMF in the rotor, and then rotor windings, reactance, and rotor resistance, and then short circuit. Okay, so this is, let us denote them R1, X1, XM, RC, and this is E1. Let us say number of turns is N1 is to N2. Now you see, in this particular circuit, in the rotor side circuit, what happens is, the EMF which is induced, okay, that is S times of E2. And what is E1? We know E1 is 4.44 is the RMS value, okay, phi S F number of turns and T. Okay, similarly E2 is 4.44, now phi S and turn. Okay. Now this phi S is F is nothing but the supply frequency, what I mean. But this is when this EMF will be induced when the slip value is 1. That means at the starting. Now when the rotor starts rotating, okay, so the flux cutting action will reduce, due to which the frequency of the induced EMF will change, or it will reduce. Or in other words, we can say that the frequency which is induced in this particular rotor circuit will be S into F of S. Okay? So that's why we have to write the rotor EMF which is induced is S times of E2. Okay? Now this is X2 into S. Again we know X2 is nothing but 2 pi F of S into L2. Now again you see this inductive or this reactance is when the rotor is at the starting, when the rotor is not rotating. If the rotor starts rotating, the frequency will change and this will become S times of X2. Okay? So this E2 and X2 values are at the starting values. Or at any other slip, we have to multiply with that slip. Okay? And here we have R2. Now you see R2 is resistance, and resistance does not change with the slip. The frequency does not depend on frequency. Now the current that will be flowing here will be I2. The current that will flow here will be I2 dash. This is I0. This is, let's say, I1. And this is my supply Vs. So this is the equivalent circuit, okay, of induction motor. Now, this particular equivalent circuit is not enough. We need to reduce it so that we can analyze the induction motor. Okay. Now you see in transformer what happened. Both the sides, the frequency were same, and there were no mechanical, output. There was no mechanical output. Electrical energy was there in both the sides. But you see here what happens. This particular stator side is electrical energy. This side, it's mechanical energy plus electrical energy. And this is air gap. So the power, first of all, the power that is generated here, let us say air gap power. Now this air gap power is transferred to the rotor and then it is converted to useful work. That means mechanical energy as well as electrical energy. Now you see, this is the electrical energy which I have shown. This is not the mechanical energy. So the electrical energy or the electrical output here is nothing but the real power will be the loss at the resistance. That means I2 square R2. This is the electrical loss. But where is the mechanical power in terms of electrical energy? So, in other words, we cannot directly, refer this particular circuit to the stator. Why? Because that mechanical part is missing. You see here, rotor, the current that is given input to the, you see the air gap, okay, or the air gap power. This air gap power will be something like I2 dash whole square R dash. Now what is this R dash? This R dash is definitely not R2. It should be more than R2 because the real power that it is transferring from here to here is not only this, there are more. Okay, there is some mechanical power involved also. Now how to find that? Okay, to find that, the technique what we have to do is we need to remove the dependency of the frequency from here. That means what I'm trying to say is I have to, if I need to refer it this side, I have to make this independent of slip. So I know that I2 is equal to SE2 by R2 square plus X2 S whole square, right? Now, by keeping the current same, I don't want to change the current, but I need to change, I need to remove the S here. So what I can do is I can bring this S to the denominator, and what will happen is R2 by S whole square plus x2. See, the equation is same. The value of I2 has not changed, but what I have done is, instead of writing SE2, what I have done is, I've removed the S from this particular thing, and I've kept the S here. Okay? The moment I do this, now S value is very small. Okay, S value will be smaller at rated load. So you see R2 by S will be very, very big. So R2 by S is very, very big, and you see I2 square R2 by S will be big. So this is not only the ohmic loss. So now what I have done actually here is, this circuit is not the only the electrical circuit of the rotor. This is the representation of the electrical as well as a mechanical circuit of the rotor. And since you see now the frequency, this is a term which is dependent on frequency, this is a term which is dependent on frequency, and both of them are f of s. And this is an independent term of frequency. Now I can refer it. Okay? Now when I refer it, what will happen is, I can remove this. So E2 will become E1 if I refer, as simple as that. Okay? So this I2 will become I2 dash. And that's it. So this is my equivalent circuit now. Okay? So that is the reason why we have R2 by S, not only R2. So R2 by S represents the complete air gap power. So the PG I can write it as I2 dash whole square R2 by S. Now this is, you see, per unit or per phase representation what we see. If we need to see the total power, then we have to multiply this, into 3. Then we will get the total air gap power. This is per phase, whatever analysis we are doing. Okay. And now, up to here it's fine. Everything is fine. Okay. Now you see we can take better approximations also. That is, the voltage drop here can also be neglected. Okay. And what we can say is, this E1 is almost equal to Vs. So what we can do is, instead of writing them here, we can write them here also. Okay? And this Vs is parallel to this particular circuit, and also Vs is parallel to this particular circuit. Now, all in all, we can remove this also, because the current flowing through that particular part will be very negligible. So this, what is left, is the best approximation circuit. Okay? And not even this, in sometimes in questions they will say that neglect the stator impedance. So in that case, you have to neglect this particular thing also. And if you see the questions in GATE, almost in every question they will ask you to neglect the stator impedance, or they will tell you that take the best approximation case for this. Okay? So I will stick to this for timing. Okay? So that my sole reason for this lecture is to make you realize how approximations is going to make our topic on induction motor easier. Okay? So now let us see this topic, how we will analyze this and how we will make the things easier now. See, earlier what happened, the torque equation, if you need to find, that is I2 dash, or what is the torque equation? The torque that is generated, electrical torque which is generated, that is equal to, you see, PG by omega S. And what is PG per phase? Let us say per phase we are doing. Or total, if you want to do total, we can do total also. 3 times of I2 dash whole square R2 by omega S into S. Now, to find this I2, if you use the practical circuit, or exact circuit. Then this I2, see, suppose I consider some inductance and resistance here and some voltage drop here. Then I know this is my voltage supply. So what I have to do is, first of all, I have to apply Thevenin's voltage here. Okay. And once I get the Thevenin's voltage here, I need to find the Thevenin's equivalent impedance at this particular point. And then after that, I can find out the current. Now, those things or those analysis will just, make my things complex, because I know that even if I ignore these particular things, my values are not going to change drastically. So I can simply ignore this. Okay. I can simply ignore this, and I can say that my I2 dash is nothing but almost equal to Vs by R2 by S whole square plus X2 whole square root over of this. Now this particular expression is going to make my analysis so much simpler. Okay, now see this. I'll write this as V supply whole square R2 by S by omega S root over R2. Now you see, I2 square is there, so this root over will be removed. So ultimately I will have R2 by S whole square plus X2 whole square. So this is my torque. Now we are going to analyze the complete induction motor on this torque equation. Okay, approximated torque equation, which is very good enough. And this approximation is good enough for our analysis. Now you see, let me draw the equivalent circuit again. So this is my simplest equivalent circuit of induction motor. Okay. Now if I need to find out, suppose say, let me write this somewhere else. Let me write my torque equation as 3 by omega S Vs whole square R2 by S whole square plus X2 whole square and bracket multiplied by R2 by S. Okay. Fine. Now let me find out what is the maximum torque which can be developed, or the maximum torque means what? I need to find out what is the maximum electrical torque which is developed. That means we know maximum electrical torque is nothing but Pg by omega S. Or in other words, I can say that what is the maximum air gap power which is developed. So if you need to find out the maximum air gap power, now air gap power, if you see the circuit here, air gap power is developed where? R2 by S. Simple. Now we know that maximum, by applying that maximum power transfer theorem, we know that maximum power will be delivered to this particular load when this is equal to the impedance of the circuit. Okay, so I can say simply that R2 by S, when R2 by S is equal to X2, PG is maximum or PE is maximum. This is a condition, as simple as that. So this S becomes maximum torque condition. So if I put it there, what will happen is T is equal to 3 by omega S, maximum case Vs whole square. This becomes 2 times of R2 by S whole square into R2 by S. Now this will get cancelled, square will get cancelled. So it becomes 3 by omega S Vs square by 2R2 into S. So this is the situation. Okay. Similarly, what we can do now is find a relationship between torque and slip. So this is important. Okay, now let us see torque-slip relationship. So at the starting, we know that the slip is going to be 1. Okay, at starting, okay, slip will almost equal to 1. It will start from 1, then 1.99, and then 0.90, and then 0.8, or in this way it will start, the slip will decrease, okay, and it will go till s is equal to 0. So let me say that the slip is almost equal to 1. So when slip is almost equal to 1, R2 by S is is less than x2. R2 by S is less than x2 when S is almost equal to 1. Because, see, the resistance is actually very less than the reactance of the windings. Okay? Because these are copper wires, the resistance will be very less. Okay? So, if I say whole square of this, that will be very less than x square. So, what I can do is, that means my TE now almost becomes 3 by omega S Vs square x2 square. I have neglected this, okay, R2 by S. So you see, from here what we can see is my torque is directly proportional to R2, or this is the starting, right, at the time of starting. So we can say the starting torque is inversely proportional to the slip and directly proportional to R2. Okay? So that is the reason you see, if the rotor resistance is more, my starting torque will be more. Okay? Also, at starting, when S is equal to 1, my starting torque is not equal to 0. That means I should have some starting torque. Okay? So you see, when the slip is equal to 1 or NR is equal to 0 here, so I have some starting torque TS. Now as the slip goes on decreasing, this is TE at this time of starting is inverse proportional to slip. So what will happen as the slip goes on decreasing till some value, what will happen? This will go on increasing. Now it will increase up to a certain limit, that is called, this value is called TE max value. And at this point, this will happen when at SMT. And what is this SMT? This SMT is nothing but X2 by R2. Sorry, R2 by X2. Okay? Now, what will happen after that? Let us see. Now, you see, after that, we can consider is now, what we can consider now is, S is very less than 1 now. That means this value will be somewhat around 0.04 or something, or say let us say 0.2 itself, which is less than 1, okay, which is less than 1. So S is less than 1. At that time, R2 by S will be more than X2. Okay? Now the moment this happens, okay, so what will happen, you see, R2 square will be very more greater than X2 square. So now what will happen is, TE, okay, at low slip condition, what will happen? This means this area is a lower slip area. Low slip area. Low slip area. So what will happen is, C 3 by omega S Vs square R2 by S whole square, and I have ignored this X2 and I have written R2 by S here. Now this will get cancelled with the square. So ultimately what will be left? This is almost is equal to R2 into S. So here we can see that TE now at low slip is proportional to S and inversely proportional to R2. So these are no load or full load conditions. Okay, that means now this is directly proportional to slip. That means if my slip is decreasing, and suppose this is S is equal to 0 here, so as my slip is decreasing, my torque is directly proportional to slip. So what will happen is my torque will become directly proportional, and when slip is 0, my torque will become 0. Okay, so this is the torque slip characteristics. Okay, this is the torque slip characteristics of what we are talking about, a 3-phase induction motor. Now if we do not change the frequency and the voltage, but we change the resistance, so what will happen? The maximum torque value will change. Okay, so maximum, suppose we reduce the resistance, so what will happen? My starting torque will reduce. Okay, and further if I reduce my resistance, okay, so what will happen? Starting torque is directly proportional to resistance. So see, my starting torque has reduced. Also the slip at which maximum torque will occur will reduce. Why? Because SMT is equal to R2 by X2. So if R2 is reduced, okay, if R2 is reduced, so what will happen? The slip at which the maximum torque occurs will reduce. But you see the value will remain same. Why? Because TEM is directly proportional to, you see, R2 and S. So if R2 is reduced, S2 will reduce. Slip will reduce, but the maximum torque value will not change. So the value will not change, okay, but the slip at which it occurs will reduce if the resistance is reduced, will increase if the resistance is increased. That means if I increase the resistance, what will happen? So this is say R1, this is R2, this is R3. So you can say that R3 is more than R1 and R1 is more than R2. So this is the case. And in gate you may get such questions where they will tell that they've reduced this resistance or they've increased the resistance, and they will ask you the increasing order or the decreasing order of the resistance by giving this particular circuit, or they may ask any questions relating to this particular concept. Okay, so this is all about torque slip characteristics, or this is a preview of or review of whatever you say of torque slip characteristics. And at a certain point, what I can just say is this is the way to look and analyze torque slip characteristics or induction motor for gate. Okay. The next topic that I'm going to do, or what actually I wanted to relate to, is the speed control of induction motor. And you see how the analysis of speed control of induction motor will become easier for us, by understanding these concepts, these assumptions, or in other words. So now see, if we need to control the speed of an induction motor, what is NR? Okay. So you see this speed, NR depends on NS. Depends on NS. Okay. So what is the relationship between them? You see, NR is nothing but this is equal to NS into 1 minus slip. Okay. And what is NS? We know NS is 120 into F by P into 1 minus. So one easy way, I'm not going to, I don't actually want to explain or describe all the techniques to change the speed of the induction motor. My actual motive was to see what is the relation or how we can change the speed of an induction motor, or what is the relation when which is dependent on frequency. So I'm going to explain the topic which is frequency dependent. Okay, speed control technique. There are other techniques. That means if you can change the poles also, and you can change the slip also. Okay, so slip changing techniques means there are how to change the slip. We can increase the resistance or decrease the resistance. Indirectly, slip will change. Similarly, you can increase the voltage or reduce the voltage. Okay, we should not increase the voltage. Why? Because we'll come to that later. For now, you see, we can reduce the voltage. Okay, if we reduce the voltage, what will happen? The slip will change accordingly. Okay, so slip changing techniques are there. What I'm more interested is to check how my speed control technique will depend on the frequency. Okay, so now you see, if I increase my frequency or I can reduce my frequency. So if I increase my frequency, what will happen? If I decrease my frequency, what will happen? Speed will increase in this case, speed will reduce in this particular case. But I also need to see what is going to be the effect if I am going to change my frequency. Okay. So let us first say what will happen if I reduce my frequency. See, we know that any electrical machine, okay, whether it is a DC machine or induction motor, you see, or let's say it's a transformer, flux will flow into it, okay? And flux, you see, the relation between flux is induced EMF is proportional to frequency into flux, okay? Now, if we neglect the stator drop, we can say that supply voltage is almost equal to the induced EMF, okay? Now we can say that my supply voltage is proportional to F into phi. Or in other words, my flux is proportional to V by F. Now what will happen? I told you earlier that we should not increase this voltage by keeping the frequency constant. If we increase the voltage here, what will happen is my flux will increase. Okay? And this is the maximum value of the flux. If it increases, what will happen is flux is nothing but B into A. Now if my area is constant, so what will happen? Flux density will increase. If flux density increases, there will be high core loss. Okay? High core loss. Both eddy current as well as hysteresis loss is, directly proportional to this B, which is flux density. So the moment I increase my flux without increasing the area, what will happen? The flux density will increase and saturation will come. If saturation comes, there are lots of losses. Okay, the BH curve area will increase. Okay, so I do not want to go into that topic. What I want you to realize here is that I should never work my machine more than the maximum flux. That means into saturation area. I should work at max the breaking point or the maximum value. This maximum value is nothing but it is the breaking point or the most higher value of the linear region. If flux increases more than this, that means it enters into the saturation region. If it enters into saturation region, then I will have more losses. Okay. So I should not increase my voltage by keeping frequency constant. If I need to increase my voltage, I have to increase my frequency. You see, I have to increase my frequency such that flux remains constant. Okay. Now you might think that, so how can we apply high voltage in a particular machine? So that is the reason. If you see, if we need to keep the frequency as 50 Hz constant and we need to apply a machine where high voltage is required, At that time you may think that yes, my flux will increase. So how is this going to run, and there will be losses? But you see, if my phi increases, now I told you that phi is equal to B into A. Actually my B should be constant. So if my phi increases, my area should increase. That's why you see the transformers where the high voltage transformers will have a core which is having a higher area, okay, or bigger transformer. If the voltage reduces, the size of the transformer reduces. Okay, so the voltage has everything to do with the size of the transformer. I hope you got it. Okay. So ultimately, what I want you to understand or realize is that since we talk about one machine, in that particular machine, area is going to constant. So if area is constant for a particular machine, so our flux should be constant, right? So that we do not want flux is equal to B into A. Area is already constant, so flux is directly proportional to B. I don't want my B to increase. So in other words, I don't want my flux to increase. Now you see what happens. Now we know that flux is proportional to V by F. Now if I reduce my frequency, what will happen? By keeping my voltage constant, what will happen? The flux will increase, which I do not want. Okay? So in that particular case, I have to reduce my voltage also. So the technique to reduce the speed by reducing the frequency is possible only when V by F is constant. Or else, if we do not follow V by F constant while reducing the frequency from 50 Hertz to 40 Hertz, let us say, what will happen is there will be very high losses, okay, and the motor will become inefficient, okay, and there will be heat losses, and which is not good actually, okay. Now let us say the V by F is constant. Now let us analyze it. So one thing what I have explained it that if I need to reduce my frequency, I have to keep V by F constant. Or in other words, V by F constant or V by F control method is nothing but for reduced frequency. Okay. Similarly, you see, second method is frequency increase. If I increase my frequency, what will happen? My flux will reduce. If my flux reduces, I don't have any problem. At least saturation is not going to be there. Okay, induced EMF may reduce, but even then I don't have any problem. So at the time of increasing the frequency, I don't mind even if my V by F is not constant. So increasing the frequency, V by F need not be constant, but you may keep it constant. So now let us consider, or let us write it down, that in this particular, let us analyze. In this case, V by F is not constant, but in this case, V by F is constant. Now let us analyze this. That means let us find out the torque relationship, torque slip relationship. So torque is, we know, is equal to 3 by omega S. Now we are going to see both at the time of starting as well as maximum case starting. So at starting, what will happen? We know that it is almost equal to, we know that this particular things, that is T starting will be V1 or Vs square R2 by S. Yes? So at the starting, what will happen? At the time of starting, X2 will be more than R2, so we can remove X2 square, we can remove R2 and multiply it by R2 minus. So this is going to be the starting case. Okay? Now you see, V by F is constant. Now you see, this term depends on frequency, and let us say at starting the slip value is almost equal to 1. So we can write this as TE is, or let me modify it here itself. So we can say that, or we can remove this S. because at starting S is almost equal to 1. Okay. Now you see, this x2 is proportional to supply frequency. Omega S, it is also nothing but 120 F by P. Okay, so one F term will come here, one F term will come here. So I can write this. This is independent of frequency. I can write this is proportional to Vs square. Now this is a frequency term will come here, and a frequency term will come here. So F square, or in other words, F cube I can write. So ultimately what I can write now is, this is proportional to V by V square by F cube. Now we know that V by F is constant, so this ultimately becomes V by F whole square into 1 by F. Now since V by F is constant, I can remove this V square, and I can say that my starting torque is inversely proportional to frequency. That means if my frequency reduces, my starting torque increases. Similarly, let us see T max value. So T max, we know we have 3 by omega S V square, and this will become, you see, R2 2R2 by S whole square, and this whole square will be R2 by S. This will be cancelled. Okay, so ultimately it will become 2R2 by S, and we know R2 by S is equal to X2. So instead of writing R2 by S, I can write X2. So now this is my maximum torque value at the maximum case. Okay, so this is 1 by F. This is first case. Now this I can say that this is V by F whole square, or this is constant, right? So this becomes constant. That means my T max is not going to change if I keep V by F constant and reduce the frequency. Similarly, T, what else we can see? For high sleep, that means when S is very, very less than 1, so at that time what will be my T? That means low sleep. For low sleep, let us see. That means when S is very, very less than 1, in that particular case, 3 by omega S V square by R2 by S and whole square will get cancelled. So sleep will come here. So, and the sleep we know it is Ns minus Nr by Ns. So sleep is inversely proportional to frequency. So at that particular case, what will happen? So it will be, this will be proportional to frequency, and this will be inversely proportional. This will also be constant. So it will become V by F whole square, and which is constant. So you see, so third one is not much important. Okay, so this too is sufficient for us to analyze. Okay, so now let us see what will happen. So if I draw the diagram for this, it will be something like this. Say this is the first case. Here F is say 50 Hertz. Now, if my frequency is reduced to 40 Hertz, what will happen is my starting torque will my starting torque will increase. That means here, somewhere here, my maximum value will not change. That means it will go somewhere here. Same value. It will be something like this. Now you see, this is for first one, S1 is equal to 0. This is S2. See, since my frequency has reduced, so the slip or this is NS1, this is NS2. Since my frequency has reduced, ns2 will be less than ns1. So that is why it will end here, that will end there. Okay. So this is going to be the situation. So this blue one is say 40 Hertz. This is, so you can analyze this particular situation. Similarly, now let us see what will happen if I increase my frequency and V by F is not constant. At that particular time, what will happen? T is starting is proportional to, you see, V square by F cube. Now, here V by F is not constant, but V is constant. In other words, I can say only V is constant. So if V is constant, T is starting is inversely again proportional to F cube this time. Okay? And T max, you see, is inversely proportional to 1 by F square. So T max is inversely proportional to 1 by F square. That means now, as my frequency increases, my starting torque reduces. And my maximum torque value also reduces. So that means, if I can draw it here, suppose this is the case 1, NS1. Okay? Now for, let me draw it properly. Suppose this is the first case and this is NS1. Okay, say this is for frequency F is equal to 50 Hertz. Okay, now I'll increase my frequency to say 60 Hertz. So if I increase my frequency, what will happen is my maximum torque as well as starting torque value both will reduce, and it will be, but my synchronous speed value will be more. Synchronous speed is more, but you see my maximum torque has reduced, starting torque also has reduced. Okay. Similarly, at some other value, I will have something. So these are the, you see, torque slip relationships at different frequencies for both reduction of frequency and increment of frequency. And this is very, very important for you to understand, and you see, gate questions will come from this particular concept. I hope you got this concept. So with this, I conclude my explanation. Now let us see some questions on this particular topic. That is, I will take a question. There are many questions from this topic. I'll take a very good question, which is a 2003 gate question. Okay. So let me read out this question before that. So this question, it says, a three-phase induction motor is driving a constant torque load at rated voltage and frequency. That means the first line says that a three-phase induction motor has a torque TL is constant. Now it says that if both voltage and frequency are halved. So if both voltage and frequency are halved, you see the V by F is constant. So I can say V by F is constant here. Then the following statements relate to the new condition. If stator resistance, leakage reactance and core loss is ignored. As I have already told you that in gate questions you will have the best approximation case, which is the example is this. So they have already ignored the stator impedance drop and also the core losses. Okay. So the first sentence what they say is, the difference between synchronous speed and actual speed remains same. First statement says omega S1 minus omega R1 is equal to omega S2 minus omega R2. Now this is what they have said. Now we need to find out whether it is correct or not. So let us derive it. Okay. So first thing we know that what is omega S1? Okay. Okay. So now let us see how to derive this. So we know that omega S1 minus omega R1 in the first at first I have already told you this will be S into omega S1, and this should be omega S2 into omega S2, okay, and this should be S1 into omega S1. Now let us find out the relation between S1 and S2. You see, they have said that a torque load is constant, or we know that TE1 is equal to TE2. Now, this load torque at loaded condition, my slip value is very, very small. So, if slip value is small, what will happen is R2 by S is very, very greater than X2, or whole square is very, very greater than X2. So, I can say that this becomes 3 omega S1, okay, V1 square R2 by S whole square is cancelled. Okay, so this is T1, and this side I also will have omega 2 R2 by S2 V2 square. This is S1, omega S1 and omega S2. Now, it is also said that the voltage and frequency both are halved. Okay? So, if voltage and frequency both are halved, what will happen? So, you see, this omega is directly proportional to frequency. So, you see, R2 I have cancelled here, 3 cancelled. So, S1 will go to the denominator. Go to S1, I can write it here. S2, I can write it here. So, S1 is equal to V2 by V1 whole square into omega S1 by omega S2 into S2. So, this is what I can write. Now, V2 I know is half of V1. And omega S1, you see they are, you see this is directly proportional to frequency. Okay, so I can say this is omega S1 by half of omega S1. So that means this is twice. So 1 by 4 into 2 into S2. So 2. So S2 is nothing but 2 times of S1. This is what we have proved. So now if we put the values here, okay, so we know omega S1 and this I can write, S1 I can write, let me put it here. So S2 I can write it S21. Okay, and omega S2 I can write it as omega S1 by 2, and this 2 and this 2 cancelled. So S2 omega S2 can be written as S1 omega S1, which is this. So you see the difference of the speed has not changed. Difference has not changed. So the first statement is, true. The first statement is given that the difference between synchronous speed and actual speed remains same. So this first statement is true. One is correct. Let us see the second statement. They say that air gap flux remains same. Now this we have already discussed, that flux is proportional to V by F. So in both the cases, V by F is constant. So if V by F is constant, my flux will be same. So second is also true. Third one, the stator current remains same. Now you see this is also we need to find it out. Okay. So current, to find out the current, let us see. We will consider the best approximation circuit. The best approximation circuit is this. Vs R2 by S and X2 will be here. So I2 or stator current is equal to I2 or I stator also you can write is nothing but V supply by root over of R2 by S whole square plus X2. Now here again we can neglect this X2. So if we neglect this X2, almost I starting is Vs by R2 S or S I can bring it up. So this is it. So you see, so first case, in the first case if we see, IS1 is Vs1 into S1 by R2. Second case, IS2 is Vs2 S2 R2. Now Vs2 I know it is half of Vs1 and S2 I know it is twice of S1. Now this 2 and this 2 cancel, so ultimately IS2 I can write this as equal to IS1. So that means the starting current is also same. So third is also true. Let us see the fourth statement. So the fourth statement is the per unit slip remains same. Per unit slip means omega S minus omega R by omega S. That means for the first case, omega S2 minus omega R2 by omega S2. Now you see omega S2 is not equal to, this is not equal to this. But this numerator is equal, but denominator is not equal. That means what will happen is, this ratio or this expression of the per unit value in both the cases will not be same. That means the fourth statement is wrong. So in that case what happens, there are four options, that is, all the statements are right. Second option is 1, 2 and 3 are right. Third option is 2, 3 and 4 is right. Fourth option is 1 and 4 is right. So we know that 1, 2 and 3 is right, 4 is wrong. That means our answer will be option B, which is 1, 2 and 3 is right. Okay. So see, this is an example where the approximations are vastly used, and if you do not apply these approximations, it will become very, very difficult for you to analyze and answer this question. So by this particular example, I want to stress on the importance of understanding how to take the approximations and what is how to analyze after taking the approximation. So by this I hope that this will be useful for your gate preparation, and this will benefit you and save your time. So best of luck for your preparation. Thank you.